Great. Thanks for coming out, everybody. It's good to see you all here. So what we're going to talk about today is check fraud. And if you're like me, you need a little bit of a refresher, beginning with, what's a check? So it turns out checks are these pieces of paper that your bank prints out in a stack, and they mail them to you. Then you write on them and give them to another person who then sends the check to their bank, and their bank sends it to your bank, and it's all done. Checks. Next question is, if you're like me, do people use those? And the answer is a resounding yes. I'm always shocked by the widespread use of checks, even today. Pop quiz, does anybody know what the most prevalent form of B2B payments in the United States is? It's checks. Smartphones have helped to usher in kind of this new generation of check usage, because now it's really easy to take an analog kind of paper check, take a picture of it, and get it into the digital world without too much hassle. So that's an easy thing you can go do. So along with all this widespread legitimate usage comes fraud, because anywhere there's an opportunity, there's a bad actor looking to take advantage of that opportunity. We see that in check fraud very much. Do I have a click? Can I just click this? Okay, yeah, good. So how big of a problem is it? Well, it turns out it's quite a large problem. According to the FBI, it's about an $18 billion problem. 60% of every fraud attempt across all FIs is check fraud. 47% of all FI losses cumulatively is due to check fraud. The list goes on and on. So my team and I, Q2, we're building a solution to all of this. We're building that solution by primarily doing two things. One is we're building a network that connects disparate and isolated deep domain experts in a material way. The second thing we do is we train an ensemble of computer vision-based classification systems, semantic segmentation objects, such a manner that that ensemble of classifiers represents the culmination, the union of all of the disparate and deep knowledge that exists across the members of that network. So what are we going to do today? Well, first thing we're going to do is we're going to take a deeper look into check fraud. What does it really look like kind of out in the field? We'll characterize that. Second thing we'll do is we'll go into more detail about our solution, machine learning-based solution that leverages network effects. And then finally, we'll talk about how we expand that network, because there's nothing more frustrating than building something of value and then having the set across which you spread that value be minimized, right? We want to maximize that set. It's very important to us. How do we do that? We'll talk about it. So first things first, what does fraud look like? Well, it turns out, I can tell you what it doesn't look like. I saw this movie like 20 years ago with Tom Hanks, and there's this guy who dresses up as an airline pilot and kind of flies around the country cashing checks one place to the next before they kind of catch up with it. Check fraud doesn't look anything like that anymore. But it's just as prevalent as it was, 50 years ago. Today it looks very, very different. Vastly sophisticated broad-scale social engineering attacks that involve all kinds of different networks. So it's a very complex problem, and it exists in many different manifestations. But one of the most popular is, it follows the arc that I'll lay out for you now. So we begin with like a broad-scale kind of social engineering communication that goes out to a bunch of people on any platform you prefer. It looks something like this. Dear sir or ma'am, I represent company X. Sounds awful official, right? We require your assistance in a financial matter. All you need to do is take this $2,000 check and deposit it into your account, with your smartphone. Then wire $1,800 of those dollars to this other downstream account. That's our accounting department. And in exchange for your services in this financial matter, you get to keep the extra $200. And almost no one falls for that, but invariably people do. Like, they're out there. That's why this kind of stuff works. The stories get worse. We see fraudsters targeting young people, first-time account holders on platforms like Roblox, Instagram. We've even seen instances where people are tricked into doing work, weeks worth of work, right? So they go do that work, honest work, right? They're doing it. And then they expect to get paid at the end of that. They get this check, turns out to be fraudulent. Not only are they not getting paid, they're getting paid negative dollars, right? So it's a terrible experience. Foments a large degree of financial hardship, and it's just a terrible experience across the board. So What do you do about a problem like this? I always do the same thing. I go find the people, the individuals, the institutions who have the problem the most, and I learn from them. That's what we do. These individuals, what they are, they're teams of fraud analysts, kind of distributed across the country, different geographies, different institutions, all different shapes and sizes. What did we learn from them? What did they teach us? Well, it turns out some of the things that we learned were things that we could anticipate, right? Check fraud shares a bunch of characteristics with, broadly, a lot of other different fraud types. So you see anomalies around application access. How does a person typically interact with a system? How do they gain access to it? What do their logins typically look like? Well, there are anomalies there. There are also a bunch of other anomalies around the details that are associated to the transaction itself. So anomalous transaction amounts, velocities, so on and so forth. At a certain point across all these discussions, we began to hear very curious comments. Hey, look, here's a fraud that's interesting to us. If you look at the font here, it looks odd. Here's another instance. If you look at this check, look at the image of this check, you can see that it's been photoshopped. So what we began to realize after hearing comment after comment like this from different banks, different financial institutions across the country, what you end up with is a realization that there's deep signal in the pixel contents of these images themselves, right? And what we're left with is, how do we pull out those details? How do we pull them out? What makes this difficult are several things. One, every bank sees different things. And two, it's a very, very hard problem to develop mathematical models of all the intricate details that these human experts are able to kind of pull out of these images. So to add a little color to this, we'll look at a couple of examples. What does this look like? What kind of things are we seeing out in the field? So one team shared with us some really interesting insights. The first time I saw any of these, I was pretty shocked. What they noted was that there's a very high degree of correlation between individuals taking pictures of checks off of a computer screen and check fraud. And it happens a lot. There's a strong correlation there. So interesting results. Different team of experts, isolated from the first. Different observation. What they found was this. They said, hey, look, we noticed that there are these signatures that we see come across the wire on these fraudulent checks, and they've all been manipulated. It appears that the bad actors are stacking fonts on top of each other to try to trick our systems. These are the words that the analysts use, and it was very surprising to me. So what you end up with is you see signatures like this, and this signature it's very unique. What we noted was that that very signature showed up in different attacks that were unrelated to each other, different checks, different users, completely independent attacks. Nonetheless, they share this very particular signature. Different team, different geography, different business. What do they see? Another signature. This appears to be a random scrawl to me. Like, I can't tell the difference. I don't know. It's like some curved lines. This is anything but a random scroll. Like the last signature, this is a very particular signature that we see recurring again and again. Different attacks, different bad actors, different institutions, different checks. What else do we see? There are relationships between the components on an image. So if you look at the font in the date field, well, that's different than the font in the pay to the order of field. You can see that pay to the order of field it's been manipulated. All the fonts are different, and lo and behold, we look at the signature down there. We see these things again and again. So what we're left with are some fundamental challenges related to all of this. One, how do we build mathematical models that represent all of the deep institutional knowledge that all of our thousands of members of our network kind of hold in their brains? How do you do that? Hard problem. How do you connect those disparate insights across all of those experts in the network? And then finally, as I mentioned before, how do we scale that network out? There's nothing more frustrating than having a valuable solution to the problem than being limited with respect to the audience that can receive that solution. So what do we do? Disparate insights, isolated experts that don't work together. Well, we build a network that materially connects all of them in such a manner that it makes it trivial for these experts to share directly with us, my team and I, the deep insights that they're able to gather by looking at fraud after fraud, check after check, hundreds of them. 2, what do we do with that information once we collect it? Well, we train ensembles of computer vision classification systems, semantic segmentation systems. We train them on the images and all of the information that our network shares directly with us. But we're left with one challenge, right? If you look at this network, it's small. There's a lot of trust in that network. They're sharing plain text check images with us by design, by necessity. We need to train our computer vision algorithms on those plain text images in order to build up kind of the culmination of all that deep institutional knowledge across the nodes in the network. We have to do that. But here's the thing. Checks, they contain a bunch of sensitive information, really sensitive information. Names, addresses, checking account numbers. I've seen social security numbers written on checks. I don't know why, but it happens. So a ton of sensitive data kind of comes out over the wire. And turns out we don't need to take ownership of any of that sensitive data, any of that PII, in order to do our job, which is does this image of a check look like fraud? We don't need, I'll say that again, we do not need to know that the address on a check was 123 Shady Lane in order to determine whether or not that check was likely fraudulent. So what do we require? What we require now is a mechanism by which we can extend functionality all the way out to the edges of our network, all the way out to any consumer of our API that does 2 things. 1, it completely obfuscates all of the sensitive information, all the PII in the image itself. It makes it go away. It is not visible to us. 1. 2, and just as critical as the first, that obfuscation event has minimal to 0 impact on our downstream classification accuracy with respect to our ensemble of classifiers. How do we do that? Protopia helps us do that. It's actually a quite simple process. If you traverse this document kind of from the left to the right, what do we begin with? We begin with this original check image. And prior to this, in an offline process, whenever we went to go train that ensemble of computer vision algorithms, what do? We embedded, we're a Python shop, so we embedded a Python process from Protopia deeply into the architecture of our deep learning topology, in such a manner that this process sees everything during train time. After training is wrapped up, this Protopia process produces an artifact. That artifact is called a stained glass transform. We ship that artifact all the way out across our network to anybody who wants to use our API. What that stained glass transform does is what you see on your screen right here. You take an original check image, you pass it through the stained glass transform on your premises. You haven't touched our API yet. What you end up with out of that transform is this character noise that you see in the middle of your screen here. That's actually what the checks look like. You cannot recover anything human readable from that. But our computer vision classification systems, they can recover everything they need. So you obfuscate the image. You send it out over the wire, our API. Our ensemble of classification semantic segmentation technique can do all the things that they need to do to be as good at identifying check fraud as, again, the culmination of that entire network of experts. And then we respond to our caller, having never seen any of the sensitive data that you very much want to protect. Okay, so what have we done? We began with a really hard problem, check fraud. We learned about what that looks like. We talked about how we built a solution to that using network effects, machine learning, transformer-based computer vision. And finally, we talked about how we expanded vastly access to that value by using Protopia AI's stained glass transform solution. So here to talk a bit more about Protopia, stained glass, and how that entire process works is Eiman.
Thank you, Jesse. So what problem exists in this scaling of the network that Jesse's talking about is really a part of a much broader problem around data accessibility, right? In order for Q2 to deliver the value of that model that they trained to all of these potential customers of theirs, they need to get access to the data on which they are going to make the predictions, right? And this is a problem that even as recently as July this year, Gartner still poses as one of the top problems for AI deployment for many companies. Now, combine that with the rise of data-centric AI, which indicates that really the value you're going to get from spending money on machine learning and AI will come from the quality of the data you have access to, and you have a pretty hard problem now. And this problem of data accessibility and the value that is tied to that happens both before training a model and, as in the case of Q2's example that Jesse just explained, after a model has been trained as well, because you need to both get the right data to the right trained models, and you need to get the right data to the people that are going to train those models. So the question really becomes, what is this data accessibility problem costing you? And that translates into, on the vendor side or on the part of the enterprise that's building the models, it translates to what new value could you be delivering if you could get access to real data? It translates to what machine learning models could you be building and training, again, if you could get more real data. And on the consumer side of the machine learning algorithms, again, whether it's within the same enterprise or external, what efficiencies could you improve if you could use machine learning algorithms like Q2 fraud detection on the real data that you have access to? What new revenue could you create if you used machine learning data with your real data? These are the questions that we try to help both the vendors and the consumers of these services, again, inside or external to an organization, get the answer to by way of the capabilities that Stained Glass Transform provides. Now, what that capability is in its shortest form is the ability to make machine learning predictions without the need to access data in its identifiable form. The Stained Glass Transform is intended to transform the data's representation to match the intent of each individual model's deployment. So in the case of Q2, right, the intent is identify fraudulent checks. So that check image on the left can be transformed into a heavily perturbed representation of that same data record, but it will still mean the same thing to the model that is going to consume it, because it has been transformed for that model's consumption, but for nothing else. We want to be able to enable performant and secure machine learning on any hardware, so it does not matter what hardware you're using under the hood, and you can take advantage of all of the security features that your hardware will provide you. And lastly, it applies to any data type. Here, we've been talking about visual examples, with computer vision being the machine learning algorithm, but I'll show you a few examples in a couple of slides of how it can apply to any data type. And more importantly, it can be deployed wherever it is that your data resides at the initial point of collection, whether it be a cloud data platform, on-premise storage server, or even at the edge. Now, how these stained glass transformations are created, just to get a broad view of it based on what Jesse was saying, is really an optimization step at the end of the model training phase. This does not require you to send your machine learning model to any particular place. We provide an extension to whatever framework you're using already to train your models. That extension runs at the end of your training pass, and it creates a stained glass transform for the model that you just trained. You take that stained glass transform, and then it gets deployed between the data source and the machine learning model that you just trained during validation or deployment. Now, the visual example we've been talking about was this check fraud case, right? But a lot of data, especially in financial services, is tabular data. You can take tabular data that consists of categorical numerical features, and you can create stochastic representations of that. That if you were to try to reconstruct what that stochastic representation looked like, the data record on the left here, which represents a married person with higher ed, certain income in their bank account, would be stochastically represented as a widowed person, incomplete ed, and a completely different number in their bank account. But to the model that's going to make a prediction about whether or not this person should get a loan, the outcome would be the same. And there are ways to actually improve the explainability of how the model performs with these transformations as well. This also applies to natural language processing tasks. And the bottom shows an example of how, again, sensitive information irrelevant to the task that was going to make predictions can be heavily transformed using stained glass transform. One last thing, and I won't get into too much detail about it, but everything we talked about with respect to transforming data records for inference data or at deployment time can be performed on training data sets as well to improve access to more real training data in order to not have the data scientist that's going to train the model have to handle large quantities of raw data that potentially has sensitive information in it. With that, I'll wrap it up, and let's connect after the session as well to see how we can help you guys. The team is here with us, and we're happy to take any questions now or after the fact as well. With that, I'll turn it over to questions. Please.
Hi, a couple of questions. So is the transformation tightly coupled with the model, meaning it's custom for every model, or is it more generic in terms of once you do the transformation, at that point it's just a representation of what was there before and model can still take it? And the second thing is, does it have any impact on the post-modeling explainability in terms of what the inputs were and which ones ranked higher in doing whatever that it was doing?
Both excellent questions. So we talked about deployment data or inference data for the majority of the conversation today. When you are creating stained glass transforms for your inference data, they are tied specifically to the model that is going to consume that. I'll add to that the explainability question. The transformations actually help you explain what the model is doing even better than without the transformations, because the transformations definition itself will specify how important the different features of the inference data that the model is going to consume are to the outcome of the model. And so even if you don't apply these transformations, if you were just to create them for the model that you just trained using the process that we have, you'd be able to use the output to explain what the model is doing. Now, on the transformations for training data, that is not tied to any model. Right? So there, on the training data set side, you are creating a new representation of the training data set that can be used to train any model that you're going to train, and it can be reused over and over again.
Hi, I just want to get your thoughts on anomaly detection models. So when you have a data set with 1 million observations and only 100 of them are fraudulent, the data set is, that skewed one way or the other. What have you seen, to be able to account for some of those challenges when you create models for that type of problem?
Sure. So that data imbalance, that particular skew, that's a problem that never ever goes away. It's part and parcel to dealing with fraud. When you look across data sets and you kind of compare the set of legitimate kind of usage data that you're able to amass to the set of fraudulent data, and the fraudulent data, it will always be vanishingly small compared to the other set. So we deal with this a bunch. Anomaly detection helps with that a lot, because when you're doing anomaly detection, it kind of doesn't matter what fraud looks like. You really need to know what normal looks like, right? So it's a way to kind of take that data imbalance and invert it. We aren't always able to do that. So clearly, in instances where we're able to make an explicit determination, build explicit models of fraud, which we do from time to time. This is no exception to that rule. Then, we feel the kind of pain of that data imbalance more acutely, and we have several mechanisms by which we deal with that. One of them is we utilize network effects. We get as many participants in our expert network as possible. We make it as easy as we can on those participants to share with us their deep insights. That's a mechanism by which we can increase, that really tiny data set. But it's always domain specific. How do you go get more data? How do you build systems that don't require more data? So these are questions that we always ask, and we deal with in different ways.
Okay, thank you.
All right. Thank you.
Thank you.